Hey everybody, welcome back. We're going to start on section 13 now. We're talking about how do we model or how do we find the appropriate model for a specific function. How do we look at its pattern? So this is going to look kind of similar to what we did before. We've got this data here. We're going to look at the context of data and look at the appropriate function to model this situation. So we're going to look to see, okay, what kind of pattern can we see? So I notice here we've got days 1, 2, 3, 4, 5, 6. Those are increasing by 1 every time. They're an even increase. And if I look here, the difference between 15 and 20 is positive 5. From here to here, it's also positive 5. So if we notice this difference, this rate of change on this first label, we call this the first difference, is constant. If the first difference is constant, that first difference tells me that it's a linear model. Will be appropriate. Just like x to the 1 is a linear term. Let's look at this one. So for Mr. Kelly, he's also increasing by 1 every time on the x value. So let's see what the y values are changing at. So from 6 to 8 is 2, 8 to 12 is 4, 12 to 18 is 6, and 18 to 26 is 8, 26 to 36 is 10. We don't see a constant term yet, so we're going to take to the next. So if this was the first difference, now we're going to look at the second difference. So from 2 to 4 is 2, 4 to 6 is 2, 6 to 8 is 2, 8 to 10 is 2. So now we've found a constant, which tells me it's a second difference. If it's a second difference, it's a quadratic model. And that's because x to the 2 is a quadratic. All right, let's look at this one. Again, he's increasing his days by 1 every time. Let's find his changing over that time. So the first difference here from 8 to 13 is 5, from 13 to 30 is 17, 13 to 35 or to 65 is 35, 65 to 124 is 59, and 124 to 213 is 89. We certainly do not have a first difference, so let's look at our second differences. From 5 to 17 is 12, 17 to 35 is 18, 35 to 59 is 24, and 59 to 89 is 30. So again, we don't have a second difference. Let's look at a third difference. 12 to 18 is 6, 18 to 24 is 6, and 24 to 30 is also 6. Here's our constant term. So this tells me the model that we're going to use is going to be a cubic model to model this information, because a third difference tells me that it's x to the third. Okay, let's look at this last one. Here, I'm looking, okay, from here to here is 2, from here to here is 1, but from 3 to 5 is 2, 5 to 7 is 2, and so on. So it's really important that when we look at those average rates of change, that we're looking at values that have the same increment. So we're really only going to look at the values that go from 1 to 3 to 5 to 7, okay? So that means we're going to look for their corresponding y value. So let's look at the difference. Here's 6, from 89 to 95 is also 6, 95 to 101 is also 6. So this is a first difference, which means it's going to be a linear model. Okay? All right, so let's talk about a geometric application. So if we're talking about the idea of perimeter, so let's say like this was x plus 6 and this is x, that would, in order to find the perimeter, we would just be looking for x plus 6 plus another x plus another x plus 6. This perimeter, this idea, is a one-dimensional idea, where if I took the entire perimeter and I laid it out, it would just be one dimension. It's a length. So because this is a one dimension, it's one dimensional, we call this a linear model, meaning it would be like x to the 1. Okay, let's look at area. So again, like if we call this x and this x, let's call this, I don't know, 8 and this is 6. If I was looking for area, the area here would be, okay, 2x plus 8 times 2x plus 6, right? But we also know dimensional here means we're looking at the length times the width, or the base times the height. This is a two-dimensional model, which tells me this would be x squared is our terms. So this is going to be a quadratic model. Okay. And then lastly, our volume. So we know it's not just length It's not just width, but it's also the height or the depth. This is a three-dimensional model. So we know that because it would be give me an x to the third number, if these were all variables of x, this would be a cubic model because it's three-dimensional. All right, let's talk about how do we talk about a restricted domain? What does that look like in a practical application where x cannot actually be anything? Okay, so let's look at this. A bottle rocket is set up on a picnic table. Can you envision it? When the firework detonates, it will shoot straight up and come back down. The height of the bottle rocket is modeled. So here we go. Here's our model. It's modeled by h of t equals negative 16t squared plus 64t plus 3. Now, algebraically, if I'm looking at this, let's finish this out, where t stands for time and h stands for the height of the rocket. So algebraically, t can be any number, right? But practically speaking, if t is time, can time be negative? It would happen way before the bottle is launched, right? Or the bottle rocket is launched. So let's kind of keep this in context. So it says find h of 2. So what does that mean? So let's go ahead and use our graphing calculator. So go ahead and take yours out. Go ahead and push pause until you can get your graphing calculator out. I'm going to pull mine up. So we've got our graphing calculators here. We're going to go to y equals and input negative 16t. Instead of t, we're going to use x squared plus 64x plus 3. Okay, so we're going to graph this, and it looks a little weird. Let's make sure that we can get our window to look the way we want it to. So in your calc, to change your window, okay, so we're going to kind of look at the numbers that we want it to. We can see here that the x values that we want to look are going between 0 and 5, and it goes up to about, looks like maybe 10. So let's change our window. So we have an X max. So you're going to hit window, which is next to the Y key. X max, we're going to have be positive. Let's do positive 5. Let's have our X minimum be 0. So we're going to change this here to 0. X max is 5. Okay. The scale will go one at a time. That's fine. For our Y minimum, let's have it be 0. And the Y maximum, we're going to have be 100 because it can go pretty high up. I'm going to leave. So let's go ahead and graph it now. That looks a lot nicer for us, okay? So when I'm looking at that window, I can see pretty much what we're looking for. This is the bottle rocket here at the table. Here's our bottle rocket here and where it ends, okay? So how do we find h of 2? So this is a new hack. Go ahead and write this down. If I want to evaluate h of 2 without using the table, here's what you do. You're going to hit trace and then just click the number 2 and hit enter. And it finds, hey, when x is 2, y is 67. So h of 2 is exactly 67. What does it mean at this context? Well, this means in 2 seconds, the height of the rocket is 67 feet high. So if we're talking about a restricted domain, remember that the domain in this case is talking about our independent value, which we know is t, which is time, okay? So is there a restriction to the time that we're talking about here? Well, in reality, because this is a real life situation, we can't have negative time, and it's also not helpful for us to wait, minutes or even hours or days after the rocket has landed back on the ground or back on the table. So we're going to figure out, okay, what time did it launch? Well, it launched at 0 seconds, so we know it starts at 0 seconds. And we want to know how long did it take before it reached back down to the ground. So we're going to find that 0 where it hits back down. So you're going to go second, trace, find the 0. Remember, so we're looking for our zeros. Our 0 is going to be over here. I'm going to put my cursor on the 0 for now to start. So there it is. So I'm going to put it to the left of that slightly. And then I'm going to move it slightly down a few to the right. And then I'm going to hit enter again. And we get, hey, y is 0 when 4.046 seconds is x. Okay. So let's look at the restricted range. Remember, range is going to be the height that we're talking about. So remember that starting value, that height is going to be 0. And we want to know the maximum height. So we're going to find a maximum of this graph. So you're going to go second trace maximum, option 4. So we're going to put our cursor where I think the maximum is. It's about right here. But now I need to find the left bound, so I'm going to keep clicking a couple to the left of it, hit enter. And now I'm going to move it over a few to the right, hit enter, and hit enter again. And here's my maximum at 2.00000, or sorry, when at the max here, it's 2 comma 67. So that's when x is 2 or time is 2, the height is 67. So actually our range is 67. Okay. And then what's the average rate of change? Remember, average rate of change, AROC. That's our F of B, which is 3, minus F of A, which is 2, all over 3 minus 2. So I know here, F of 3, how do I find that? We can hit trace 3. And that tells me, hey, when X is 3, Y is 51. So it's 51 all over 3 minus F of 2 we already found was 67. So 51 minus 67 we know is negative 16. 3 minus 2 is 1. So that's negative 16. And then let's talk about what this is in the context of the problem. So this means, hey, for that average rate of change from 2 to 3, so from 2 to 3 seconds, the rocket, because it goes negative 16 feet, the rocket loses height 15 feet. Okay. All right, so let's get back to our notes here. So let's look at piecewise function. Remember, so a piecewise function is a disjointed function where we have a few different parts of different functions all put together as one. So this graph is the price of a high school yearbook. The yearbook sells for $40 for the first 5 months of school. So you can kind of envision those announcements. Hey, the yearbook's $50. It'll go up after a certain price after every month after that. Okay. So what is the domain? So we know, hey, what is the domain? The domain is what X can be. In this case, X is the number of months after school starts. So I know the month that starts at 0 months. That's the very first day. And then from there, if I put in any value, it goes all the way up to 9. But here it's an open circle at 9. So we say it starts at 0 and it goes to 9, but doesn't exactly complete 9. So it's just shy of 9 months. The range in this context are the Y values. But notice we don't have a continual range. We have these gaps. So we know the range can be 40. The range can be 50, Y can be 60, Y can be 70, and Y can be 80. That's our maximum price. But it's not going to be an interval in between, so we list them as separate individual values. Now, how do we find F of 5.5? Well, when I input 5.5, that's right here. I'm going to follow this up to the function. I see it right here, and I follow it back. The price is going to be $50. So what does this mean? After 5.5 months of school, the price of the yearbook is $50. All right, that's it. I'll see you back in class.